Before we look at the noise performance of digital communication systems, we need to review the Gaussian probability density function. This is information you should have picked up in the probability and statistics class, but this is going to be a review of that information, concentrating on the Gaussian probability density function. The Gaussian probability density function is important because it turns out that when several independent factors contribute to the results of some kind of random experiment, or in our case a random signal, the results are very often described by the Gaussian probability distribution due to an effect called the central limit theorem. Anytime you take a random process or a set of random processes, and they are operated upon in some kind of linear fashion, amplification, addition, that kind of thing. The result of the random processes tends to move toward a Gaussian distribution. So often random signals are taken to be Gaussian. Just as an analysis tool, if nothing else. This is the equation for the Gaussian probability density function, using lowercase f for a probability density function, and our variable is x. So this is the probability density function for the variable x. Has a term 1 over the square root of 2 pi times sigma x squared. This sigma x squared is known as the variance. That's sigma x. When it's squared, it is the variance. Variance, I won't spell out variance, but I'll remind you of that. Times e to the power of, and then we have a minus, and then in the numerator x minus mx. This m with the subscript x is the mean value, that is the average value. That's the mean value of the random variable. And again, the variance shows up as in the fraction for this exponential function. So it's minus, we have x minus m sub x, that's squared, that's in the numerator, that's divided by 2 times the variance sigma x squared. And we can plot this as a function of x as follows. The Gaussian probability distribution follows this familiar so-called bell-shaped curve. The mean value, m subscript x, falls right in the middle of the distribution. That's where the curve hits its highest point, and then its width is determined by the value of the variance. If you take the square root of the variance, you get sigma x. This is known as the standard deviation. So the standard deviation is sigma x. If you start at the mean value and you add 1, 2, 3 standard deviations, the curve from the bell-shaped curve is essentially back down to 0. It's not quite down to 0, but if you're drawing a hand sketch, a sketch by hand, that will be close enough. The value at the peak in the middle is given by the term that's in front of the exponential. You put in x equals to the mean value m sub x, and then you get e to the 0, which returns a 1. So that gives you the peak, the highest value. If you move 1 standard deviation off of the mean value, then the value of the bell-shaped curve is dropped to 0.6, approximately 0.6 times its peak value. You move 2 standard deviations off, it's down to 0.135 times its highest value. And you move 3 standard deviations off, it's essentially down to 0. well, good enough for a hand-sketched curve anyway. Okay, so this, if you change the value of the mean, you simply shift the location of the bell-shaped curve left and right. If you change the value of the variance, you change its width. So if you have a smaller value for the variance, the curve will be more narrow. That's not a very good bell-shaped curve, but it'll be more narrow and it'll be taller. And if you make the variance larger, so it's wider, its peak value will be less and it will be more spread out. It'll be wider. The two terms that completely describe the shape of the Gaussian probability density function are the variance, which shows up two places in the equation, and the mean value, which shows up one place in the equation. As I just described, the Gaussian probability density function is completely described by two factors. M sub x is the mean value, describes where the center of the curve falls, and sigma x squared is the variance, which describes the width of the distribution and also its height. The area under the probability density function is always equal to 1 for a valid probability density function. If you want to look at the areas under the various parts of the curve, they're shown below. Here is the Gaussian probability distribution curve with its mean value m sub x right in the middle, and the square root of the variance, which is the standard deviation. So we've got 1, 2, 3 standard deviations to each side of the mean, and I used those lines just to break the curve into these 1, 2, 3, 4, 5, 6, 7, 8 portions. If you go beyond 3 standard deviations, the area under the curve is 0.00135. That's for all of the area to the outside of the 3 standard deviations. Between 2 and 3 standard deviations, 0.02145 for these two areas. See, we're looking now. Oh, I'm sorry. We're looking at the area underneath this portion of the curve, being 0.02145. Under the next portions of the curve, 0.13590. That's these areas under these portions of the curve. And the two central portions of the curve each are 0.34130. So that's these larger areas under the curve. Now the total area under the curve is equal to 1. If you add up these numbers, they get pretty close to 1. There's some rounding error involved as well. But this is a good approximation for the areas under these sections of the curve. And the areas under the curve are important because those are what we evaluate to find the probability of events. The probability of an event is found by finding the area under the probability density function curve. So if you want to know the probability that a random variable takes a value, in this case greater than the value x naught, that probability that's expressed here as the probability that x is greater than x naught. We find that by finding the area under the curve to the right greater than the value of x naught, and we integrate that area, and that will give us the probability of this event occurring. And probabilities of events are always numbers that lie between 0 and 1. 0 would be 0 probability, never happens. 1 would be unity probability, always happens. Consequently, the area under the entire curve is equal to 1, presuming this event always happens. And so what we need to do is integrate the area underneath this curve as shown here. So we could write that equation, and that equation would look something like this. The the probability that the random variable x is greater than a specific value x naught is found by integrating the area underneath the probability density function between x naught and infinity. And here is the equation for the probability density function. And if we knew specific values for x naught and the variance and the mean, then conceivably we could evaluate this integral and find that probability easily enough. Unfortunately, there is no closed form solution for this integral. It has no closed form antiderivative. Consequently, there is no equation we can write in evaluating this integral. What we are forced to do is rely on numerically tabulated values in a table. That's what it means by tabulated. This integral has been numerically evaluated and the results have been tabulated for us. The area underneath the Gaussian distribution is presented to us in the form of a table that I will show soon, but the function is described as q of x. So here is the Gaussian distribution with a mean value of 0, so its center portion of the curve rests at x equals 0, and it is unit variance, so sigma x squared is equal to 1, and if sigma x squared is equal to 1, the square root of the variance, which is the standard deviation, is also 1. So it has a standard deviation of 1, and in 1, 2, 3 standard deviations to the right of the mean, it's essentially down to 0, and then 1, 2, 3 standard deviations to the left of the mean, the bell-shaped curve is essentially down to 0. The tables give us the area underneath the curve to the right of the value x. So we have a table, and we look up the input to the table is the value of x. We read in the table the area under the curve to the right of that value of x. And since the total area under the curve has got to be equal to 1, that will also give us the area to the left of the curve as 1 minus the number from the table q of x. Now, and the table itself, to save space, they only give half. The maximum number it will give is 0.5. It goes from the mean, from the value of 0 to the right. This is the table for the area underneath the Gaussian distribution. This is q of x, the area to the right of the value x underneath the Gaussian curve. So it's very small numbers, I understand. You may or may not be able to see it in the video form, but in the notes you will find this PowerPoint, and you can look at the table more closely in that file. This table is very well known. Any number of sources will give it to you. I'm sure you can find it on a copy of it on the internet very easily. And the way this gives us the value of q of x is the area underneath the curve, and we look up the value of x, which runs, first of all, the first digit runs down the rows. It starts at 0.0 and increases, and the highest number in this form of the table is 2.9. And then across the columns is the second digit of accuracy. So we start at x equals 0.000, I'm sorry, 0.00, and we get the area under the curve is 0.5. And then the next entry is x equals 0.01, and the entry is 0.9460. And if you wanted to do x equals 3.3, too big, beyond the range. How about x equals 2.3? You would read down to 2.0, and then you go 3 columns across to 2.03. Sorry, we wanted to do 12. Yeah, let's do 2.03. 2.03, and then you would read the value. Okay, so this now is the table used to find the areas underneath the curve. But this has been tabulated for a mean value of 0 and a variance of 1. So it's 0 mean unit variance. But if our Gaussian distribution does not have a 0 mean and a unit variance, how do we find the area? Well, it's accounted for by this simple calculation before we apply the number to the table Q. Let's say we have a probability density function with some value mx and then some value for the variance sigma x squared, so we can sketch the distribution function. We start at the mean value and you go 1, 2, 3 standard deviations to the right, and that's when the curve has dropped to 0, and then 1, 2, 3 standard deviations to the left, and the curve has dropped to 0. So if you know the mean value and you know the variance, you can sketch this bell shape, and then locate the number, the value that you want to know the area to the right of that value. And we can find that when applied to the table for Q of x by taking Q of the value you were interested in, x naught, minus the mean value in the numerator of this fraction, and then divide by sigma. Now this is not the variance, this is the standard deviation. This is the square root of the variance, so it's sigma x in the denominator. And then this will evaluate to a number inside the parentheses, and we can look up the value in the Q table, and that will give us this area under the curve for any Gaussian distribution, as long as we know the value we're looking for the area, and we know the mean value, and we know the variance. Consequently, we know the standard deviation. So briefly some numerical examples. Let's say we're given a Gaussian variable with a mean m sub x equal to 10. So the mean value is equal to 10, and a variance sigma x squared equal to 4. Well, that makes the standard deviation the square root of 4. That's 2. So when we sketch the curve, we start with the highest value at the mean, which is 10, and we go 1, 2, 3 standard deviations. Standard deviation is the square root of the variance, so it's equal to 2. So we go 10, 12, 14, 16. To the right of the mean, that's when the curve is essentially 0. And we go 3 standard deviations to the left of the mean. That's 8, 6, 4. That's when the bell-shaped curve is essentially 0 as well. So we can sketch this shape. So that's a Gaussian variable with a mean of 10 and a variance of 4. What is the probability that the random value takes a value greater than 12? So we want to know the area under this portion of the curve for x greater than 12. So using this expression Q of x minus m sub x divided by sigma x, that's going to be Q of we're looking at the value 12. The mean value is 10, and we're dividing by the square root of the variance. So the square root of 4 is 2. 12 minus 10 is 2. 2 divided by 2 is 1. So we look in the table at the value Q of 1, and that number will give us the area underneath this portion of the curve, and thus the probability of this event. So Q of 1.0 is what we're looking for. So we look down the value, the x value, to the value of 1.0. So it's 1.00. So the number we're looking for is 0.1587. So the probability of, under those circumstances, of that event occurring is 0.1587. Another numerical example, given a Gaussian variable with a mean of 10 and a variance of 4, so it's the same curve we were looking at before. What is the probability that the random variable takes a value less than 7? So we look at we sketch 7 on the scale, and we want to know the area to the left of this point. That would give us the probability that the random variable is less than 7. Well, the table doesn't have values to the left of anything. It only has values to the right of a certain number. But we can take advantage of the symmetry of the curve and see we are 1, 2, 3 units to the left of the mean. So that's 3 units to the left of the mean. If we go 3 units to the right of the mean, we will have an equal area underneath the curve for x greater than 13. So let's use that trick. We're looking for the probability of the random variable being less than 7. The table doesn't give us that, but we can easily look up the probability of the event being greater than 13, and since the curve is symmetrical, those areas will be equal and the probabilities will be the same. So the probability that it's less than 7 we can find by finding from the table. We can read the value, the probability that it's greater than 13. That will give us the same thing. So that would be Q of 13 minus 10 divided by, again, the square root of the variance. So divided by 2. 3 divided by 2 is 1.5. So we look up in the table the value for 1.5. So we look up on the table the value of Q of 1.5. Read down the value of x till we get to the value of x equals 1.5. And the table reads that the value of the area is 0.0668. Here is a third numerical example. Let's start with the same Gaussian distribution, mean of 10, a variance of 4. And now I want to know the probability that the random variable takes a value between 12 and 14. So that's the area underneath the curve between the value of 12 and the value of 14. Well, the table doesn't give us a number for this particular region. What it gives us is the number for the area for x greater than 12, and we can also look up the value for x greater than 14. So if we take the area to the right of 12, which is given by this expression, Q of 12 minus 10 divided by 2, and we subtract out the area that is greater than 14, that would be Q of 14 minus 10 divided by 2, what we are left with is the area that we're looking for. So 12 minus 10 over 2 would give us Q of 1, minus Q of 14 minus 10 over 2 would be Q of 2, and we can look those two values up in the table. So Q of 1 minus Q of 2, Q of 1 is 0.1587, Q of 2 is 0.0228, and subtract one from the other, and we get the probability that the random variable lies in the range we were looking at is 0.1359. In this example, I want to work the table the other direction. Given a Gaussian random variable with a mean of 10 and a variance of 4, so we're looking at the same one, what is the value of the random variable where the probability of x greater than x naught is equal to 0.25? Okay, so we're going to work the table the other direction now. I'm looking for the value of x where the probability that x is greater than x naught. I'm looking for the value of x naught, so that probability that x being greater than x naught is equal to 0.25. So I want the value of x naught that would give us the area under this curve equal to 0.25. So I know the mean value, I know the square root of the variance, I know that, so that's the standard deviation, I know that, and I know the area that I'm looking for. What I don't know is the value of x naught. So if we look at the table, see, we want Q of x naught minus 10 divided by 2 to be equal to 0.25. I'll look at the numbers in the table to find the value 0.25. Well, I don't find exactly 0.25. I find these pair of values, 0.2514 and 0.2483. And it looks like 0.25 lies in between these two entries. Now, you could probably do some kind of linear interpolation and get closer if you wished. But I'm going to presume that it'll be close enough if we're halfway in between these two. So if I take the average of these two entries, then halfway between these two entries would be about 0.25. Well, see, this is 0.6 between 0.67 and 0.68. So the entry halfway in between I'm going to take is 0.675. That would be halfway in between. So I'm observing that Q of 0.675 is about 0.25. Now that's a bit of an approximation, but we'll live with it under these circumstances, I presume. So Q of 0.675 is about equal to 0.25. So now I've got to make 0.675 equal to everything inside these parentheses. So you set x naught minus 10 divided by 2 equal to 0.675 and solve for x naught. That turns out to be x naught is equal to 11.35.